Good morning, everyone. Welcome again to DevDay Stockholm. It's a pleasure to be here, and there is actually a bit of sunlight today, so that's amazing. So my name is Julian. I'm the AI evangelist for EMEA, and I have the pleasure of doing 3 talks today. So busy day, and you will get tired of me before the end. I can promise that. My first talk today is about deep learning for developers. And this is what we're going to cover. So very quickly, we're going to show why deep learning is just not for PhDs and world experts. Everybody in the room can do it. Who's a developer in the room? All right, everybody. OK. Who can read and write 50 lines of Python? Come on, everybody. Come on. It's Python, right? OK, so the good news is all of you can do deep learning, right? But stay around. I will show you how. We'll talk really quick about infrastructure, because obviously we need to have infrastructure to train the models, and there are some options I want to discuss. Then we're going to look at some common neural network architectures, and they all have weird names, and some use cases, and some GitHub projects that you can use out of the box to do some pretty fancy stuff. Then we're going to talk about Apache MXNet, which is a deep learning library that AWS likes to use to build their own projects, and we're going to talk about it. And of course, we'll do some demos, and hopefully the demo god will be with me today. And at the end, I will share some resources to help you speed up your learning and really get involved with this stuff. So if you listen to some people, they will tell you AI is really very complicated, right? It's too complicated for us, for you and me. Okay, I'm not a genius, far from it. So no, I cannot do AI, right? And when they say that, when they say, oh, it's very complicated, it's dark magic and so weird, what they really mean is usually is you're not very smart and I am, so I'll do it for you, but you have to pay me lots of money. And as you know, that's not the AWS way. The AWS way is you do stuff, right? We build building blocks, we'll build services, we build APIs, and we try to make them simple, and you use them. Okay, so I want all of you to do this stuff, not just some experts. So the fact is that AI is just math, code, and chips. So it is a bit of science, sure, especially if you want to work at a low level, if you want to build deep learning frameworks, if you want to invent new deep learning models, sure, you need to have a math background and some computer science and statistics, etc. But as a matter of fact, a lot of people already do that, right? All the research teams in the world are building those models, so they're taking care of that part, and we can actually build on top of that. So for 99% of use cases, even 99.9%, we don't have to invent new models. We have to find the model that's going to work for our business case, and we have to adapt it. So in that context, AI and deep learning are really a lot of code, right? And some infrastructure work and some cloud work to get it done. So while we're on the subject of infrastructure, basically, you have 2 options when you want to run deep learning workloads. Okay, the one I'm sure you know about is obviously to use GPUs. Okay, and we support the latest NVIDIA generation of GPUs, which is called Tesla, and those are super powerful. We used to have GPU instances before. They were called the P2 family. Now we have the P3 family with that new NVIDIA chip. And yes, they are extremely powerful, and you can have from 1 to 8 GPUs in the same instance. Okay? And they have crazy statistics and performance numbers. And for massive data sets, they are pretty much mandatory. Okay? In the training phase, if you have tons of data, GPUs still win. Okay, but there is a second option, and we like you to save money, as you know. And I would hate that you use GPUs when CPUs could actually do the trick. And we have another option, which is using the C5 instance family with the Skylake architecture. This came out a few months ago. And compared to the previous C4 family, well, it's more of everything, more cores, faster EBS throughput, more memory, and especially the new Skylake architecture, which supports AVX 512, so vectorized instructions that are super useful when you do machine learning and deep learning. So you get a really, really nice speed up, not only because these are faster instances, but also because of that instruction set. So another important factor is how they compare in pricing, right? So if you look at the C5 pricing compared to P2 and P3, well, you can see there's a big difference, okay? So sure, like everybody else, I love to play with the P3 16XL, especially since I don't pay my AWS bills, but you do, right? So I want you to be aware of those differences. So, you don't always need a P3 16XL. Maybe one of the C5s is more than enough to do the job. And as you can see, there is a massive price difference, okay? So again, for very large jobs, for training at very large scale, yes, you will need GPUs, and the P2 and P3 families are probably what you need here. But if you want to train on smaller data sets, small to mid-sized data sets, and if you want to do prediction, then actually the C5 family is a much better deal, okay? You will not get a huge performance increase by doing prediction on GPUs, especially if you predict, let's say, image per image. And so C5 becomes a much better option. If you throw Spot instances into the mix, then here's an example. Well, this becomes even more apparent and obvious. As a matter of fact, today, it is very difficult to grab P3 instances in the Spot market, right? So there is a lot of competition. So as you can see, basically the spot price market is the on-demand price, so that's not a very good deal. But if you look at the C5 example, you can get very, very large discounts on C5s in the spot market, okay? So what that means is, here in this example, as you can see, C5 would be 20 times cheaper than one single P3. So for the same budget, you could have 20 C5 instances, and these are big ones, right? C5 18XL. So you could have 20 servers running prediction instead of just one GPU instance. So I can guarantee that no matter how many cores and no matter how powerful that GPU is, you will get better performance and better scalability by using C5s. Okay? So keep that in mind. Really the rule of thumb here is, if you need to train on large data sets, use GPUs. If you need to train on small to mid-sized data sets, you could actually get a good result with C5, especially if you add a lot of C5s, if you do distributed training over those instances. And for prediction, in most cases, CPUs are going to be the better choice, from a performance point of view and a cost point of view. Okay? So I love GPUs, but they're not always the best choice. Okay? That's my message here. Okay, so enough about infrastructure. Let's talk about models, actually, and how we can use them. So probably you've seen this before, right? This is probably the most popular type of architecture today. It's called the convolutional neural network architecture, or CNN. It was invented a while ago by Yann Lequin, a French guy, who's running the Facebook AI lab now in Paris. And basically, these types of network are extremely good are detecting, classifying, working with images. Okay, and the reason for this is because of this convolution operation, which is, it's a mathematical operation that helps you extract features from images, as you can see from that example on the right. We start with an image, and gradually we shrink it to smaller images, but keeping important features. Okay, I'm not going into the details of convolution today, but ask me questions at the end if you want. And we're reducing dimensions, keeping features, so literally squeezing the image into something smaller, but something that has still vital information about what the image is. And we shrink it again and again and again until we get to something pretty small that we can classify using a standard fully connected network. And this architecture, this is really the most basic architecture, but as you will see, we can extend that to do much more clever things. Here's an example of a customer using CNNs for a real-life purpose. So the customer is Expedia, right? Major travel website. And their problem is pretty simple. They have a ton of images, a ton of hotels, and they want to automatically pick the best image for a hotel page, right? Because, of course, if you show nice images, this helps boost conversion. People are likely to book hotel rooms. So some images are really good, like these, for example, right? They look nice. They give you a positive image on the, pun not intended, on the hotel. Some other images are not so great, right? And you have to keep in mind that some images are user provided, right? People go to the hotels and they take pictures and they upload them. So that's how you end up having 10 million images. So which one do you pick, right? So it's very nice to know there is actually a toilet in the room, right? So it's useful information, but I'm not sure that's actually what I want to see. And the nuclear reactor, well, if you're a nuclear physicist, that's interesting, but for the rest of us, not so much. Okay, so how do you pick automatically the best image, right? And the data set is growing all the time, as you can see. So what they did is they took a pre-trained network, okay? So they took a pre-trained CNN network, pre-trained CNN, trained on a very large image data set, right? And the interest in taking a pre-trained network, I'll show you an example in the demos, is that, well, it's pre-trained, so you don't have to train it. So you save time and money, right? Expert did train it, so you can just reuse their work and, as we call it, fine-tune it, adapt it with a relatively small number of images to your own business problem. It's a very powerful technique. So they took 100K images from their data set, so that's 1%. They labeled them, so it's still a bit of work to label 100K images, but it's doable, right? 10 million is not really doable. And they retrained that network using the GPU instances and a deep learning library called Keras. They retrained the network on those 100K images, right? And they were able to obtain really good results. And they put this in production, and now automatically the images that are displayed on the hotel pages are selected by this model. Okay. If you want to know more, this link has the full video from one of their developers at a tech conference, and it goes into all the details of how they did it. And it's a surprisingly small project. We're not talking 6 months. It's just a few weeks, because reusing a pre-trained network obviously saves you a lot of time. Okay. Here's another example. It's called object detection. So object detection is going one step further than classification. Detection really wants to figure out what's in the picture and where. Okay? So as you can see, we have bounding boxes around the objects, and we have labels, and we have confidence scores. Okay? So it's probably a little tiny here, but yeah, it's a motorcycle 0.997%. Okay? Here. And as you can see, we can figure out a whole lot of different objects and everything. So object detection, and well, as you guessed, those two samples here, they are based on GitHub projects, which are MXNet based projects, and these are actually MXNet implementations or of state-of-the-art detection networks that are called RCNN and YOLO. And YOLO means you only look once, which is a really cool name. And that's the real name of the research paper too, right? So who said they had no humor? So you can literally go to those GitHub projects, grab the models, and use them. They give you the pre-trained models to use directly. Okay. So if you have that kind of detection business problem, you can solve it very easily, right? So long as the objects that you want to detect are present in the data set that they use for training, right? If you want to detect, I don't know, icebergs and moose, right? Just a guess. Maybe they're not in the data set, so you have to check, right? You have to check. So object detection. Going one step further, we have object segmentation, which is detection plus finding the outlines. Okay, and here, this is a project by, it's an open source project by a company called TuSimple. They build autonomous driving systems, and so it's quite important to them to figure out where cars are and where pedestrians are. And they actually open sourced their implementation, which is again MXNet based, and it's called the Mask RCNN network. And it's a really, really fancy architecture. And again, you can just grab this and run it in an afternoon on your own system. Okay, so this is really cool. If you attended Adrian's talk earlier, and I'm sure most of you did, he talked about high-level services, right? Amazon recognition, etc., etc. And recognition is great. But sometimes you have specific problems like this that recognition cannot handle, maybe one day, but not today. And you have to go a level deeper and build that thing yourself. But it doesn't mean you have to build everything from scratch, right? Because the community has been implementing those networks in MXNet and providing you with pre-trained networks. So you can actually save a lot of time. So it's a good middle ground between using recognition or trying to do everything from scratch, which is a big project. And talking about TuSimple, like I said, they build autonomous driving systems. And last summer, they drove the truck, or I should say the truck drove itself autonomously for 300 kilometers in the southwest of the US. Okay, and this is based on MXNet model. Okay, so it's not science fiction. It's not just geeks having fun on GitHub and releasing stuff. It's real companies using this stuff to solve real problems. Here's another example, face detection, right? Again, recognition, Amazon recognition can do face detection, but if you want to build it yourself or add new attributes that are not present in recognition or customize it in any way, well, you could do that. There's this MXNet Face project that uses a CNN architecture to do face detection. So not only detecting where faces are, but for every single face, providing you with a ton of attributes, right? And it's fair to say there are more attributes than in recognition. So, good for them. Interesting project. Here's an example of using this to do serious stuff. It's an organization called Thorn. And what they do is pretty serious work. Their mission is to find missing kids, right? And specifically missing kids that are abused and sexually exploited. So that's pretty grim stuff. And the way they do this is they go and they build a database of missing kids, first of all. They try to age the kids, because if the kids disappeared when he was 10, let's say, maybe now it would be 15. So, kids don't look the same, right? At 10 and 15. So they're modifying the picture to try to have a realistic picture of the kid today. And they look for that face on the darkest spots of the internet. Okay. They do this with one of our partners, which is called MemSQL. And MemSQL builds using AWS infrastructure and services. They built a platform to do this, that analysis, the aging process, and the analysis process between the pictures and the pictures you would find on the internet. And it's successful because it's an ugly stat, but I mean it's positive and negative. But they find 5 kids every day, right? So then they can hopefully send the cops and rescue them. So it's an example of, again, using AI to do serious stuff. It's not just, again, geeks, right? It's in this case, life-critical stuff. Here's another project. This one is silly and geeky. I'll give you that. It's called real-time pause estimation. So you look at a video feed, and you try to identify the position of the human body. Okay, so shoulders and knees, as you can see, and you can do this in real time on a video feed. Okay, and it's not tracking; it's really looking at every single picture. Okay, once again, this is based on MXNet. You can grab and run that model this afternoon if you want. Okay, it's available. So as you can see, CNNs are, they're not just to detect dogs and cats. Okay, that's fun. It's a good, it's a good first tutorial to run. But you can go with much more complicated architectures, and we have a lot of customers who use this for real purposes. Right? I gave you a few examples. Thorn and Too Simple, and we have many more in many different industries. So this is really production stuff. Another architecture that you run into quite often is called LSTM, and that means long short-term memory networks. That's a very confusing name because how could it be long and short at the same time? So they're long. Yeah, it's a weird name. And I keep calling them LTSM anyway, but so the real name is LSTM. I need to get my hand around that. So they're long because they're very, very deep. They have many cells linked to one another. And they have short-term memory, which means when a neuron is predicting, it's not just predicting on the input, it's predicting on the input and a previous state. So they have memory of the previous inputs, right? But not the 1,000 previous inputs. That's why it's short-term memory. So that's a neuron right there. I'm not going to go into that today. You can thank me. The only thing you need to remember is they are good at predicting sequences, okay? Because they have memory. So if you want to do machine translation, right? It's important to work on sequences because some words are more likely to follow a given word than any other word, right? That's the way our language works. So if you remember, quote unquote, what the previous word was and what the word before that was, then you're likely to make a better prediction for that given word, okay? And as a matter of fact, this architecture is used in an open source project called Sockeye, which is an AWS project implemented by our machine learning team in Germany. And it's a machine translation tool. So the model is built, and you just give a data set. So you could provide a Swedish data set and an English data set. And you could train Sockeye to translate from Swedish to English, for example. Okay, just run this on the GPU instance for a few hours or a couple of maybe 1 day, and you would have a good model. Okay, and this is an example of German to English. Okay, it's there to grab. You could also use Amazon Translate. I guess Adrian mentioned it earlier, right? Which we released at reInvent. And the Translate is based on this, actually. It's a service built on top of this technology. Okay, so if you're looking for a language pair that is not available in Translate, and typically Swedish isn't available now, well, you could use Sockeye and get to the same accuracy just by training for maybe 1 day on a GPU instance. Okay, pretty cool project. And the last one I want to touch upon is crazy. They're called GANs. Generative adversarial networks. And all the networks we've seen so far, they try to make sense of the real world, right? We look at images, we look at text, and we try to figure out what that is, okay? GANs are something else. GANs are generating new data, right? Such as this. So you have to convince yourself that these people do not exist, okay? These faces have been generated using a data set called the celebrity data set, okay, and they do not exist. These are not real people, right? Which, would fool literally everyone, I think, right? These are pretty high-res pictures, okay? So this is not an MXNet project, but it's a GAN architecture. And what about this one? So if you look at the bottom left corner, you see, sorry if it's a bit small, you see what we call a semantic map. So a semantic map is the equivalent of what a 5-year-old kid will draw, right? If you told that kid, draw me a road and a tree and a car. and you can color everything, right? So they would say, okay, well, I have some trees, and I have some people here, and I have the sidewalk here, and here's the front of the car, and that's the road, okay? So no detail at all, just outlines and different colors to show, of course, the limits. Okay, so you could draw that in paintbrush or on a piece of paper, scan it, run it through that pix-to-pix model, and you generate this. Okay, and this is high res. So just go to that page. You can zoom on that picture. You can read the license plates. It's fake, obviously, but these are proper numbers. You can zoom on everything, and it looks very realistic. And this is generated, right? So once we learn how to do this on video, fake news are going to be very, very interesting, right? But at reInvent, our technical conference in Las Vegas, we had a customer, Autodesk. Probably you're familiar with those guys, right? They do CAD applications. And they do what they call generative design. So instead of designing, let's say, car parts or motorcycle parts or mechanical parts, like they would do traditionally, right? They just give the constraints. So they say, okay, the piece should be this size, it should have this weight, should have this volume, should have this mechanical strength, blah, blah, blah. Just write the equivalent of the semantic map, right? Just mechanical and physical properties, okay? And the system will actually generate the piece. Right? You can find that video on YouTube. It's called Generative Design. Just look for reInvent Generative Design, and you'll find it. If not, just ping me. I'll send it to you. And the system comes up. I think they showed an example of a motorcycle part. You know, the swing arm from the motorcycle, the part that ties the chassis to the rear wheel. If you're a biker, you know what I mean. If not, that's okay. It's a fairly large mechanical part, right? And they designed it that way, and it looks crazy, It's because the system came up with a shape that probably no designer would have ever invented, and yet it's lighter and stronger, and probably less expensive to manufacture than anything they could have designed. So now we use this kind of technology to actually generate mechanical parts, right? Pretty crazy. So this is a quick run through. What you can do with neural networks and CNNs in particular. So let's look at MXNet. So what is MXNet? MXNet is a deep learning library. It's available for multiple languages, which tends to be an advantage compared to other libraries. So you could do Python, Scala, C++, Julia, R, and probably more that I don't know about. It's an Apache project, so it's not owned by anybody. It's just driven by the Apache committee. It's portable. It runs obviously well in the cloud, but it runs well on smaller devices like a Raspberry Pi. And if the demo gods are with me, I can show you this. And it scales very well. So if you have very large data sets, if you need to train for a longer period of time, you can actually throw more GPUs at the problem on MXNet and have linear scaling, right? So if your problem takes 16 days with one GPU, if you use 16 GPUs, you'll get pretty close to 1 day, right? Which again is a major benefit compared to other libraries. So MXNet, the MXNet API supports all the typical building blocks that you would need to build all the kinds of networks that I showed you. Right, so we can do obviously image recognition, we can do machine translation, text processing, etc. So you have high-level symbols that you can use to build complex networks that look like the ones I showed you. Just a couple of recent features. Now you can serve predictions from MXNet. So it's not just training and building models. You can very easily deploy them behind a web app and serve predictions from an HTTP endpoint. Okay, so I don't know if I would use this in production. I don't know about the scalability, but for testing, for integration environments, this is really great because just with one API call, you can deploy the model with behind an Nginx web server and start serving requests. Another cool feature is called ONNX. Basically, it's being able to exchange models between different libraries. So that used to be a big problem. You know, somebody would do something really cool in Cafe, and well, if you wanted to use it in MXNet, you would have to recode the network and retrain it, etc. And now, using ONNX, you can import and export models to and from MXNet and to Cafe, the Microsoft toolkit, and another one that I'm missing. Okay, so it's good for everybody to be able to reuse the work. So obviously, we're not going to go through the full API, but I want to talk about 4 objects that are really important. Deep learning always starts with storing data, right? So once it has been prepared and clean, you need to load it into multi-dimensional arrays to serve it to the model. Okay, so we're going to see that ND array object, which means n-dimension array. Okay, to store the data. To build the models, the layers, and the weights, etc., we're going to use the symbol API, right? And we'll use some of those building blocks that you saw on the previous slide to build networks. Then we need to, during training, we need to serve the data batch by batch, right? We're not pushing the whole data set through the network at once. We're slicing it into batches and training batch by batch until the end of the data set. Okay, and we have very useful objects called iterators to do this. In other libraries, you have to do this manually. And finally, when we want to put everything together and when we want to train and use models, we're going to use the module API. Okay, so ND arrays, symbols, iterators, and modules is what you're going to see in every single example. So let's go through those 4 demos, right? So the first one is Hello World. We're going to build a synthetic data set and learn it and see what happens. The second one, we're going to classify images with pre-trained models. So no training at all, just grab a model, push some images through, see what happens. Then we're going to train 2 different networks on the MNIST data set, which is very popular. It's a good toy data set to work with. It's handwritten digits from 0 to 9, and we try to classify the images. And time permitting, I will run the same example on Keras and TensorFlow to give you a sense of the differences between those libraries. Okay, so let's get going. Okay, so I'm using a Jupyter notebook to do this. So what I'm going to do here is really pretty basic. I'm going to create a matrix, right, with 10,000 samples. Okay, I'm going to use 8,000 for training and 2,000 for testing. And each sample is a vector with 100 random floating point values. Okay, so 10,000 lines, 100 columns. Okay. And each sample belongs to one of 10 categories. And again, it's a random category between 0 and 9, I suppose. Okay? So it's fully random data. Sorry. So here are my parameters here. Okay, let's run this stuff. Okay, so like I said, 10,000 samples, 100 features per sample, 10 categories. All right, so here I'm just initializing that matrix, which I call X, okay? So 10,000 by 100 with floating point values between 0 and 1. And I'm initializing the Y vector, which is the label for each sample with a random integer between 0 and 9, okay? So fully random stuff. Okay, then I'm splitting my data set for training and validation. Okay, so 8,000 for training, 2,000, right? So as you can see, 8,000 for training, 2,000 for testing. Then I'm going to define a very simple network. Okay, so I have an input layer that I call data, right? I'm not specifying any shape right now. I'm just saying, hey, that's the input data. I have a first fully connected layer with 1024 neurons, right? And the ReLU activation function. And I have a second fully connected layer with 10 categories, 10 neurons. Okay, and that's it. Okay, so that's the super simple neural network. Input data, one hidden layer, 1024 neurons, and then the output layer with the 10 categories. Okay, and each neuron on the output layer will store the probability that this sample belongs to this category. Okay, so this is the symbol API I was talking about. I just need to build an iterator to serve my data set batch by batch. Okay. And then I'm binding the model that I defined to the iterator, initializing some parameters. And now I can train. So now I'm ready to let my model learn my data set. Okay, so I can see, and I'm training for 50 epochs, so I'm going 50 times through the data set to let the network learn. Okay, so obviously this is pretty fast here, because it's a smallish data set, very small. And I can see the training accuracy going up and up and up, so my network is properly learning, and I even get to 1, which means I perfectly learned it. And I get to for 50 epochs, and yes, I learned perfectly, so that's fantastic, right? You can have a fully crappy data set, and the network learns it. Okay, what's the catch? Well, the catch is, if I want to use now my test data set to do some predictions, accuracy is 10%, which makes sense, right? Because there is no structure at all in my data. So if you need to randomly classify objects in 10 categories, well, you'll be right 10% of the time, right? So that's the lesson here. A neural network can learn anything, okay, but training accuracy only tells part of the story, okay? If your data, garbage in, garbage out, it was true for code 20 years ago, it's still true for deep learning. So if your data set is not formatted correctly, or if it has no structure, well, there's nothing to learn, right? So be careful of training accuracy. Validation accuracy is what you want. Okay? So that's the big, big lesson to understand. So let's move on to classifying pictures. Just want to show you maybe here. I want to run it on a Raspberry Pi, but yeah, I want to show you the picture first. So I'm on the Raspberry Pi here. So this is what I want to do, basically. I want to load 2 different deep learning models. I'll show you the code after that. Just throw you the overview first. Just load a couple of pre-trained models and predict the image passed as an argument with those 2 networks. Okay. All right. So basically, what I need to do is load the model. Okay, all this code is on GitHub, and I'm not going to explain every single line. Just want to point you to the important parts. So loading a model is actually as simple as this, right? You download the model file from GitHub or wherever it is, okay, and you call that load checkpoint API with the model name, okay, and that's it. You have a model and you bind it, okay, like we did before, and you have a model ready to serve. Okay, so no training, just grab a pre-trained model and load it. Okay, I need to load the categories. I need to have the category names on which that model has been trained. And then obviously, I need to load my JPEG image into an ND array. Okay, so I use OpenCV to do this, load it, resize it, make sure the red, green, and blue channels are in the right order, etc. And then the prediction is really this, right? I call the forward API on that image that I put in an ND array. I read the outputs on the output layer. So this model has been trained on the ImageNet dataset, which has 1,000 categories. So I will have 1,000 probabilities, one for each class. So I read them, and basically I sort them, and I return the top 5 ones, I think, right? Okay, I don't want 1,000 probabilities. I want the top 5 probabilities, okay? And that's about it. And how much code is this? 60 lines, right? And I have 2 models. So, okay, when I said 50, I was about close. So if you can read and write 50 lines of Python, you can use pre-trained models and be ready to do this in literally 1 hour, okay? Even less, okay? So, and don't remember, I'm on the Raspberry Pi here, right? So let's run this. Okay, so just to show you the picture. Okay, here's the picture I'm using, okay? Okay, so I need to load the models. And these are pretty complex models. One of them, I think, is 50 megabytes, and the other one is about 200 megabytes. So it takes a while to load, but you would need to load them only once. Okay, and then I'm predicting. And it's a Raspberry Pi, so I need 4.5 seconds to do this, right? So yeah, it's not super powerful. And I get the top 5 probabilities, okay? So 96.9%, you know, there's a violin in there, which there is. And are we dead here? Oh, nice. All right, so we won't get the other one. Is that Wi-Fi dying on me? No, come on. No? All right, then it's a Raspberry Pi dying on me. Fine. Good timing. Okay, but you get the idea, okay? So you can, yeah, obviously my shell is dead here. So you can copy those models. Obviously, no one would ever train anything on a Raspberry Pi. Come on. But, yeah, come on, boot. All right, let's try that again. Okay, but you could have your Raspberry Pi or your device just reuse a pre-trained model and predict stuff. Okay, and there are ways to speed up prediction with open source libraries, etc. But of course, it is a Raspberry Pi, so you're not going to predict at 10 images per second, or you know, it's going to be a few seconds per image with those advanced network. But the prediction is really very correct, right? It's here we go. All right. Okay, so ResNet 6 seconds. Inception, which is faster and shorter, 1.7 seconds, with still a very good probability. Okay, so that's MXNet running in the embedded world. Okay, and as you can see, the models are here. So Inception is 44 megs, and ResNet is 230 megs. It's a very big network. Okay, so if you can load them in RAM, they should work. Okay, so obviously, same exact code I would run somewhere else. Okay, let's move on. Where is that window? Here. Okay, so here I'm going to do this one. So that network that I showed you, the LeNet network, the first CNN I showed you with the traffic sign, it's that one actually with a few modifications. So it's a basic network, but it does work very well. So what do I need to do here? Well, I'm loading my data set. We have a pre-existing iterator for MNIST, so that's very convenient. Just give them the file names and it builds the iterator. Here's the LeNet network. Okay, so we can see an input layer and then a succession of convolution and pooling layers to squeeze the image. And then a fully connected layer to classify it into 10 categories. Okay, pretty basic architecture, very fast to train, still pretty efficient. Okay. So yeah, we need to do this. We need to bind the model to the iterator, and then we can train. And as you can see, it's very similar code, right? You will see this in MXNet. It's always the same steps, right? So it's define a network, bind, train, and here I'm training for, is it 25 epochs, I think? Okay, so I'm training on an EC2 instance. I can see my training accuracy going up. Right? It takes about 2 seconds per epoch. Right, so we'll get to 25 in a few seconds. And then I'm going to save the model. Okay, that's all it takes. And I'm going to reuse it to predict some digits. Right, come on, go, 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 go. Are we there? Are we done? Yeah, looks like it. Okay, so we get to the 25 epochs, save the model, measure its accuracy using the validation data set. Okay, so 99%, that's quite good. And now I can predict some samples. So these are real samples that I drew, with paintbrush, because that's what real life looks like. It's ugly. You need to test with real life samples. Okay, so again, I need a small function to load my image into an ND array. The predict code is exactly the one you saw before, right? Just call forward. Okay, I need to load that LeNet model. Here we go. And then, okay, I need to predict my images. So here's my 0. And, well, it is really predicted as a 0, right? That vector you see is the 10 probabilities for each class, right? So it's actually 0, 9, 9, 9, 9, 9, 9, 9, but I think I stopped at 4 decimals, so it's rounded up to 1, okay? Okay, well, 1 is good. Yeah, pretty good. 2 is very good. 3 is great. 4, 5. So this is a very good model. As you can see, it's simple, but it's very good at this. And I have a notably ugly 9. Yep, so as you can see, even though it's a very ugly 9, and it's a lower probability, but there is no doubt, right? That's really the highest one, okay? So here's an example. 5 minutes of training on a very small data set and small images. These are 32 by 32 pixels. You can build a solid solution, right? If you could do this with a to recognize handwriting, etc., etc. Okay. All right. So just a really very quick look. I'm not going to run it, but I'm going to show you what it would look like in this other library called Keras. Okay. So Keras is an open source project. And you can use different backends. So you can use it with TensorFlow. You can use it with MXNet. You can use it with Theano. So it's a high-level API that's very popular with developers. And as you can see, okay, this is how you define a network in Keras. And again, you have the link to the notebooks, so you can replay that. It's pretty similar. It's pretty high level. And this is how you define that it's pretty much the LeNet network again. Just a few APIs, just combining layers. And then, okay, compiling it. Okay, it's not called bind, it's called compile in Keras. And then you call fit to train it. Okay, it's very similar. So you have a choice of libraries. AWS likes MXNet for the reason I mentioned, but Keras is a popular choice. Some other people use Caffe, some other people use PyTorch, etc. They will all run well on the GPU instances. Okay, all right. Okay, so now, yeah, maybe this one before. So how do you get started with this stuff? This is just a very fast overview, just to show you what's possible and show you that my 50 lines of Python promise is not fake, right? I'm not a deep learning scientist. I'm a software engineer. I learned this stuff, and I guess I could read 50 lines of Python, and now I can read a little more and do a little more. But anyone in this room can do this. So if you want proper steps to get started with this, you can go to my blog on Medium. I'll give you the URL in a second. I just wrote days ago a 2-part post, which I call the 10 steps on the road to deep learning, which are, okay, what should you learn, in what order, and how should you learn? And this is how I did it. So, it worked for me. Hopefully it's going to work for a lot of people. And, I'm happy to get your feedback on this. So some additional resources. So the top-level machine learning page at AWS, the AI blog, which has very cool content. And my post, I got a post yesterday. Yes! So it is very cool content. The MXNet website, the MXNet sources, an API which is called Gluon, which is part of MXNet, which is high level, had a lot of pre-trained models, so you should look at Gluon, and the Gluon documentation is really, really great. It's a great introduction to deep learning too. So my blog on Medium and that post that I just mentioned, that should help you get started, okay? Do not be afraid, you can all do it. All right. Well, I'm done. Thank you very much. If you have questions, I think we maybe have a few minutes for questions if I'm not too late. And then I think we have a talk. Jan, I saw Jan is over there. Jan is doing a talk on chatbots. And then I will be back with more deep learning, more notebooks, and more examples. Thank you very much.